Non, mais garde ton mail parce que tu vas
Ouais, je vais
renvoyer
l'envoyer.
un mail à tes. Ok. Ok.
Ok,
Donc là,
maintenant, je
tu
retourne dans Zoom.
partager. Non, là, tu vas nous partager.
Ok.
Tu copies le lien. Voilà, comme ça. Et ça, tu vas l'envoyer. On va couper la caméra. Ok. Retourne sur Zoom.
Là, il
La
faut
coupe juste la.
vidéo.
Ouais.
Gilles, bonjour.
Bonjour, tu vas bien, Patrick? On
Ouais, parfait.
m'entend? On m'entend?
C'est fort là.
Attends. Et là, ça va un peu mieux? Allô? On
Moi, je
m'entend? Tu peux essayer?
Ok. Gilles, il y a une deuxième personne qui est en remote,
Oui,
qui est aux États-Unis, donc on attend qu'il se connecte. Bon, d'accord.
très bien.
Et donc, toi, tu n'as pas de Chine, là, ça marche. Ok. Et donc, là, tu vois bien la présentation.
Gilles, est-ce que tu vois la présentation?
Oui, oui, je le vois très bien.
D'accord. Ok, nickel. D'accord. Donc, on attend un petit peu qui.
J'enlève ça pour être sûr que le
Oui, oui.
Hello, Luke. Do you hear me? Do you hear me? Do you hear me now, Lou? Yes. Merci. Hello, hello. I'm not hearing you. Yeah, thanks, Jim. So I think this is on your side, Lou.
Hello?
Do you hear me? I can hear you. Do you hear me, Lou?
Yes, now it's good.
That's perfect. Thank you. And do you see the presentation?
Yes.
Perfect.
Ça marche là?
Ouais. Oui.
Okay. Okay. Hi, Lulu. Welcome. I'm Patrick. Okay. And just to tell you, Armand will make his presentation for about 45 minutes. After that, we will have a round of questions by the members of the jury. Okay. Is that clear? Hello. Did you hear me?
Yes, it's clear. Thank you, Patrick.
Everything is clear for you, right? He says yes.
Okay, welcome, and thank you for being here today for the PhD defense of Armand Kassaï. I am Paola Cinella. I am a professor here at Sorbonne University, and I'm a specialist of computational field mechanics, but with application of machine learning for computational physics. And I'm going to introduce, first of all, the committee members, starting with the colleagues connected online. So we have Gilles Loup, who is a professor at the University of Liège, in Belgium, and Professor Lulu, who is an assistant professor at Yale University. Thank you for joining us today. Here in the room, we have Mark Schonauer, who is an emeritus research director at INRIA, and the two thesis supervisors, so Joël Ducteau and Patrick Gallinari, who are both researchers at ISER Lab. So Armand, you have about 40-45 minutes for presenting your work. And then we will have a single round of questions, starting with the reviewers, so the person who are online, the reviewers.
Thank you for the introduction. Hello, everyone. Good afternoon. Thanks for being here today for my PhD defense, which is entitled Scalable Neural Operators for Parametric PDEs, Adaptive and Generative Methods. So this thesis has been supervised by Patrick Gallinari and Joël Ducteau at Sorbonne University. And so in this thesis, I will mainly discuss about scalable, generative, and adaptive neural operators for parametric PDEs. And so I will first give a background on this topic, and then I will move on into the contributions. So I will first talk about generalization, then operator learning, and scalability. And of course, I will conclude with some perspectives. So in nature, we observe a lot of different physical systems, and understanding the systems has always been a key scientific problem. So first, to understand how the systems behave, and how and how the world we are living in works, but also to solve important industrial applications. So for instance, design optimization with nuclear systems, but also prototyping with car crash designs, or extreme event forecasting with tsunamis. And so the classical tool for doing this is simulation. And so to simulate physical fields, we usually rely on the mathematical modeling tool, which are partial differential equations. So in PDE, describe how a physical system evolved in space and time. So yes, the PDE explicitly models the physics. So to understand what a PDE is, we usually are given a differential operator, so here n, which acts on the solution U we are trying to predict. And this differential operator is usually parameterized by some PDE coefficient C and a forcing function F. We are also given a boundary operator B that acts on the solution and which is also parameterized by boundary conditions. And finally, we are given an initial condition. So what does it mean visually? So let's say that we are trying to solve the Navier-Stokes example, meaning that we want to understand how a physical system evolved in space and time. And here the physical system is, we are trying to predict how a fluid evolved in a domain. So on the left, we observe a domain here. And so we have to specify some boundaries conditions on this domain. And we also observe an object shape here. And on the right, we are given an initial condition here. And with some PD coefficients, we are able somehow to understand and to predict how this system evolved in space and time. And the classical solutions do not exist for that type of problems because such systems are very complex. So what we do instead is numerical simulations. So numerical simulations, they provide approximate solution of the solutions via discretization and so via spatial and temporal discretization. So on the left here, we do spatial discretization, meaning that instead of computing the solution on all the nodes, on all the locations, we will only try to predict the solution on specific nodes on this mesh. And similarly, on the right, we want to predict the solution in time, but we will only predict at some specific locations in time. So numerical simulations are very stable and they're interpretable, but they usually require human expertise and they are costly. So what we advocate here instead is to use deep learning. So deep learning, if it offers an alternative to explicit modeling, by learning the spatial temporal dynamics directly from data. So on the left, we observe here the data set. So we are given n trajectories of the vorticity equation here. And what we would like is to train a model F that is parameterized by theta. And given a snapshot UT, we want to learn a model that's able to predict the next time step solution. So neural surrogates, they have several advantages over explicit methods. They are fast and they are prior knowledge free. There are, of course, different approaches in deep learning for tackling that type of tasks. First, there are neural solvers. So neural solvers, so they rely on prior knowledge only. So they do not use data. So PINS is an example of a neural solver. There are also hybrid models where you rely both on data and some physical priors. And there are neural surrogates which rely only on data. And in this work, I will mainly focus on neural surrogates and hybrid models. And neural surrogates, they also face some challenges. So first, they generalize bad to new PDU parameters, initial conditions, or long horizons, meaning that when you train a model on a context, it generalizes bad to a new context. Also, classical neural surrogates are usually not suitable for complex grids or changes in the discretization or complex domains. For instance, here, there are some input points that are missing, or on the left, on the right, here, the object shape can change, which is complex to solve. Also, classical neural networks are usually bad at scaling to very dense mesh resolutions, which are very common for physical systems. And finally, most neural surrogates are deterministic models, but for very complex systems with stochastic and chaotic behaviors, we would like instead a model that outputs distribution of trajectories. So in this thesis, I will first discuss about generalization, and I will present JEBS and Zebra. Then I will move on to operative learning, where I will discuss ENMA, and I will conclude on how to scale these methods with ECO. So let's dive into JEBS, which is the first contribution of this thesis. So with JEBS, we try to solve the parametric PDU problem, meaning that we try to learn a neural surrogate that is able to generalize to new PDU coefficients, new forcing terms, boundary types, or initial conditions. And this is a very important task for neural surrogates, because in practical use, we usually encounter new scenarios that we would like to generalize. So on the right, let's take an example. We are given a task, so we have trajectories from the vorticity equation, and we want a neural surrogate that starts from an initial condition at t equals 0 and is able to predict the dynamics, so to unroll the trajectory. And we would like a model that is good at a high viscosity here, but also at a low viscosity. So this is a typical generalization problem. The classical way to handle that type of task is via PDU parameter conditioning, meaning that we have to give as input to the model the PDU knowledge. But for practical application, we usually do not have such information. And the other way to do it is via foundation models. So foundation models, they rely on massive pre-training datasets. And also for that type of application in real world, we do not have such data. Because in real world, data is most often scarce. And what we think instead is that in real world settings, data comes from distinct environments. So on the left, this is the COVID tracker example. So here we report the number of the curves represent a number of confirmed cases of COVID-19 across different countries. And we observe that for different countries, there are some shared patterns, but still the dynamics are very different. On the right, this is the sea surface temperature. And similarly here, we can imagine that environments correspond to different spatial locations on the map. And what we would like is a model that is able to generalize to a new spatial location at influence. And so the task we are trying to solve, parametric PDEs, are exactly the same problem, because when there are small changes in the PDE parameters, they usually are large changes in the observed dynamics. And what people usually do is they rely on classical empirical risk minimization, meaning that they train a model on massive data sets, but in a brutal way. And what we advocate for here instead is to rely on adaptive conditioning methods. So adaptive conditioning methods are neural networks that are trained on specific data sets where we observe different environments, so here and here. Here, an environment corresponds to a set of trajectories with similar PD parameters but different initial condition. And we would like a model that is able to be trained on these specific environments such that it can adapt to a new environment at inference given a new trajectory from this environment. So by fine-tuning the model very fastly on one trajectory, we would like the model to be able to handle this new environment. So to show that adaptive conditioning can perform better than classical methods, we do some experiments. So what we report here on the top is we increase the number of environments and we train an adaptive methods with foundation models and theorem baselines on this task. So we train model on in-distribution environments, and we want to see if the model is able to generalize to new trajectories from this environment. And so on the left, this is the Gray-Scott equation, and on the right, the Burger's equation. And we observe on both settings that adaptive conditioning perform better than classical methods. So here, the foundation model has been pre-trained on massive physics and is fine-tuned on our dataset. On the bottom row, what we do instead is that we fix the number of environments, but we increase the number of trajectories per environment. And you observe the same behaviors, meaning that adaptive conditioning performs better than classical methods. But what we are particularly interested in is how the model generalizes to new environments that it didn't see during training. So here on the left, we report two bar plots on Gray-Scott and Burger's equation. And so what we do here is that we use a model that's been pre-trained on 4 environments, and we fine-tune it on new environments given one trajectory. And we observe that in both datasets, JEPS has better relative L2. And on the right, we take a model pre-trained on 1,024 environments, and we fine-tune it on the new environment. So it means that on both the scarce regime and the non-scarce regime, adaptive conditioning perform better. So adaptive conditioning methods are good candidates for out-of-distribution generalization. The problem with adaptive methods is that they are expensive. So there are 2 lines of works that use adaptive methods. There are gradient-based approach. So gradient-based methods like MAML involve complex meta-training loops. So during training, they have one inner and one outer loop. So the goal of this approach is to learn a good initialization for the model such that it can adapt to new environments very quickly. So the model is pre-trained in such way. So it requires gradient adaptation at inference, which is costly. And the other way is the context-based method. So here what you do instead is that you have a context vector here that is pre-trained and that's trained in this environment specific. It is given as input to a hypernetwork that generates the weight of the forecaster that does the next time step prediction. And so here, the main problem with that type of approach is that the context size do not scale well, meaning that the number of parameters of the model increase a lot with respect to the context size. So we propose instead a very simple approach, which is JEPS. This is a context-based adaptive method, so like CODA that I just presented before. So here, adaptation is done in the parameter space. We have a neural network in blue, which is G-theta. And what we want to do is to adapt each layer of this neural network. So what we do is that we add to the parameters a low-rank decomposition matrix. So the A and B are environment agnostic here. And we modulate the weight via a context here that is environment specific instead. And so at inference, to fine-tune to a new environment, you just have to retrain this small context. And by retraining this small context, it adapts the parameters of all the layers of the network. What we propose also is a hybrid formulation. So if we have some physics that are available and they can be incomplete, we want to add it to the neural network. So it takes as input the physics model here, and here the parameters of the PD can be learned. And the neural network here acts only as a corrector. So it tries to predict the unseen edges. And so here instead, we have to use a neural ODE formulation, meaning that G theta learns a continuous time vector field. Regarding the datasets, we do experiments on 4 different datasets. So 1 ODE, 1 DPD, and 2 DPDs. And we report the in-distribution performance, so how the model behaves on new trajectories from similar training environments, and out of distribution generalization, so how the model behaves on new trajectories from unseen environments. And so here what we report is the related L2 metric, average across all trajectories from test sets and all time steps. Concerning the baselines, we consider both adaptive methods and hybrid methods. So regarding the results, JEPS is performing very well on in-distribution environments. So on the left, we report the data-driven part model of JEPS, and here the physics version, so the hybrid version. And so here what I report is how the JEPS is better with respect to the best baseline here. And we observe that on most cases, JEPS has a lower latency compared to the best baseline. Concerning the out of distribution environments, we have similar trends, meaning that JEPS is also very good at generalizing to new environments, given just one extra trajectory to fine-tune the model. We also do some comparison to existing context-based methods, such as CODA. And what we observe, when we increase the dimension of the context, the number of parameters of the model do not increase for JEPS, which is in red, while for CODA, we observe that the number of parameters increase a lot. So JEPS scales way more better with respect to the context size than CODA. So what is very interesting is the ability of the models to adapt quickly to a new environment. And we observe that JEPS scales is able to converge much more faster than CODA. So to sum up with this first contribution, we propose a method that is fast at adaptation. It is model agnostic, meaning that you can use any backbone to train the model, and it has very good scaling properties. However, there are some drawbacks. So it requires still random-based adaptation as inference, and it's pretty slow due to the null ODE formulation. So that's what motivated us to do Zebra, which is the next contribution of this thesis. So in JEPS, I said that we propose the method that is model agnostic, but more and more transformers become a standard in the literature. So meaning that we do not really need any other backbones. So, and what is particularly interesting with transformers, in particular LLMs in language, is the ability to perform in-context learning. So, and this is very interesting for us because existing methods for parametric PDs usually require complex meta training or gradient step at inference, which is expensive. So what is in-context learning? So let's suppose that we're given a prompt here with 3 sequences, sequence 1, sequence 2, and sequence 3. And the 3 sequences, they respect one rule, which is UN plus 1 equal 3 UN minus 1. And we are also given sequence 4 here. And what we would like from the LLM is the ability to uncover the dynamics, so to predict the next numbers. And we observe that somehow LLMs are able to infer the correct patterns just from the sequence 1 and 2 and 3. So the model is able to infer implicitly the parameters UN plus 1 equals 3 UN minus 1. And so this is exactly what we would like to have also for parametric PD. So instead, we have a context trajectory that has similar PD parameters that the trajectory we would like to forecast. And so just given an initial condition and a context that has similar PD parameters, we would like the model to be able to infer the dynamics. That's exactly what we try to do with Zebra. So with Zebra, we give as input to the model some example trajectories that have similar PD parameters. And we have also query initial conditions. So this is the time this is a snapshot that we would like to forecast in time. We give it to a tokenizer, and we concatenate the sequences together. We obtain a representation in sequence here that is given to a causal transformer, and the transformer is able to generate tokens by tokens the trajectory. So at the end, we obtain the trajectory here, And what we hope is that it has the same PD parameters than the context trajectories here. And to do so, rely on the VQVA first that is trained in the first stage, and then we train the llama just via next token prediction. So for quantization, we use the VQVA with CNN that is trained on regular grids. And so we obtain a codebook Z that is trained with corresponding index from entries from this codebook. And what we want then is to be able to train the model as in an LLM, so via next token objective, via negative log likelihood. And what we do in particular here is in-context retraining, meaning that the model takes as inputs a sequence where we concatenate different trajectories that share the same dynamics. And here dynamics correspond to the same PG parameters. And to differentiate between two trajectories, we include some markers, so begin of trajectory or end of trajectory markers. Regarding evaluation, Zebra is tested on 7 datasets, so 5 1D-PD and 2 2D-PD. Like JEPS, we report in distribution performance and out of distribution performance. And again, we report the relative altometric average across time and number of trajectories. And for the baselines, we consider meta-learning methods and in-context learning methods. So on the left, I will first show an example of what Zebra takes as inputs. So here, this is the combined equation. It takes as input a context prompt. So here, each curve corresponds to a different time step, so different colors. And it takes, so this as input with an initial condition, and the model is able to forecast the dynamics. So it predicts the next time steps. And we observe that the ground truth is very similar to the predictions, meaning that the model has been able somehow to infer the PD parameters from this context. Regarding quantitative results, we do some in-distribution generalization tests. And so we observe that Zebra is either the best, so in green, or the second best in blue. And what we do also in particular is out of distribution generalization. So here I report only the performance of Zebra compared to the best baseline. And we observe that in all cases, Zebra is either the best or it's tied. So to conclude with Zebra, we propose an approach that allows adaptive conditioning without gradient steps. So as inference, it does not, we do not need to adapt the model via gradient adaptation. It also has very good genetic capabilities that I didn't show here. And it's pretty competitive in terms of performance, both in distribution and out of distribution generalization. However, there are some drawbacks. First, Zebra rely on a quantization, which is not very natural for physical systems. It cannot support irregular grids, and it is pretty slow at inference. So that's what motivated us to do NMAP, which is the next contribution of this thesis. So with NMAP, we try to tackle real-world challenges where classical neural surrogates are not well designed for. So as I said, approaches like Zebra require quantization, so this is not very suited for physical systems. They cannot support complex geometries or regular meshes. So for instance, when you have in the grid some input points that are missing, or if the domain is complex with arbitrary points at arbitrary location. And so physical systems are typically defined on such complex geometries. So we require here instead a neural network that operates, so an operator that maps continuous functions to continuous functions. And this model should be robust to geometry and to discretization. And so pioneer neural operators are well suited for PDA modeling. So there are two different works that try to address this problem. So the first one is DeepNet. And with DeepNet, they take as input one trunk net and one branch net. The trunk net takes as inputs some query coordinates, and the model is able it allows us continuous evaluation, meaning that you can output at any point in the grid. However, DeepNet is not discretization free because the input function and the branch net is usually defined on some fixed sensor location. And regarding FNO, the method is trained in the Fourier space. So the model is discretization invariant. but it is not disputation free, so it is fully restricted to the grid, so to regular grids, meaning that it can perform some super resolution tasks, but you cannot evaluate on arbitrary grids, meshes, and it does not allow continuous evaluation. However, there are a lot of different works that have been that have extended those works. So we tried to overcome some of these limitations some years ago with Coral. So Coral is an implicit neural representation method that works with an encode process decode framework. And a linear is a model that takes as input some spatial coordinates and tries to map it to the physical values associated. So it allows continuous evaluation and discretization from modeling. And to learn a class of samples, what we do is that we rely on some modulation. So we train a hypernetwork via a context here, Z, that is specific to the trajectory, and it modulates the ways of the INF. So the drawbacks with Coral is that it requires greater adaptation at inference to adapt to new trajectories. It is also, as it has also been tested only on deterministic models, and it's pretty low. It has pretty low performance on very high frequency systems, meaning that when you encode the data set physical systems with high frequencies, it usually discards this high frequencies. So that's why we proposed ENMA, which tries to solve the limitation of Zebra and Coral. And with ENMA, we perform in-context generation in a continuous space. We also model uncertainty and partially observed data, and we can adapt to change in the discretization grid or in the domain. And so with ENMA, we first train the encoder-decoder, and then we train the process. So let's dive into the encoder-decoder. So ENMA takes as input any mesh, any geometry or domain. It takes as input some keys and values. So here, these are physical coordinates and the corresponding physical values. So physical value here and coordinate there. And they are given through a cross-addition module. And we also give as queries some regular latent representation, meaning that so this is learned. And the regular representation here is initialized as regular grid. And so the cross-addition modules allows to map it into a latent representation. So this allows continuous evaluation at the decoding stage because we have the same mechanism, and it is discretization free. On top of that, what we do is that we add some CNN blocks to further compress information if needed. We also use a geometry-aware attention bias, so to enforce locality in the cross-addition module, meaning that points that are very far from each other will get high attention, while tokens that are far from each other have lower attention because we have some penalty as well. For the process, so let's imagine that we give as input to the model a series of input states. So it passes into the encoder, so we obtain a latent representation Z0 to L, so we have L frames. So this is the input sequence. We give it to a spatial temporal causal transformer. And so the spatial causal transformer outputs latent context ZLDIN, which is given as an input to a spatial transformer. And so the spatial transformer will then generate all the tokens one by one to generate the next latent state ZL. So this is an autoregressive process to generate all the tokens of one latent state. So let's dive into the spatial transformer to try to understand it. So as I said, you take a context as input that has been obtained from the spatial temporal causal transformer. You give it to a spatial transformer with a mask that represents the token the latent token that we are trying to generate. We get the output of the spatial transformer. So here it says Z tilde. And Z tilde is then given to the flow matching MLP, but not all tokens are directly given. Instead, we use a scheduler that sets the number of tokens to generate at each step. So at the first step here, only one token will be generated. And we use a flow matching generation process, meaning that we start from noise, we solve an ODE to generate the corresponding token. And so at step 2, we have now a new token that has been generated, and again, we still have this context. So we reiterate the process, we give it the spatial transformer, we get the spatial transformer representation, and we have here the scheduler sets the number of tokens to generate to 5, and so 5 tokens will be generated. And at step 3, we reiterate the process until all the tokens are generated for this lattice. Regarding the experiments, again, ENMA is evaluated on 5 different datasets, so 3 1D problems and 2 2D problems. 2 1D problems and 3 2D problems. And we report 2 different types of experiments. So first, we want to assess the encoder-decoder quality. So here we report it against other no operators that work in the latent space. And then we also want to report in and out of distribution generalization. And here we restrict to regular grids because most of the neural circuits are defined on this setting. We also target 2 different tasks, which is the in-context problem. So this is the same problem than with Zebra, and the temporal conditioning problem. So meaning that we give as input some input states, and we want to infer the rest of the dynamics. Regarding the encoder-decoder quality, so we report 3 different types of results. So here, this is the input sampling, so 100%, 50%, and 20%. When there is only 20%, it means that only 20% of the input has been given to the model, and the model must predict the rest of the grid. So it means that it is a partially observed problem. And we report it on the advection problem and on the vorticity problem. And we observe that in both settings. For reconstruction, for instance, ENMA has much lower error than the best baseline, which is Aroma. So on the 20% case, it's 5 times better. And we have similar observation in time stable. Regarding neural operators, the performance on in and out of distribution generalization. On 3 datasets, advection combining Griscott, ENMA is better or it's tight. But on 2 datasets, wave and vorticity, ENMA is a bit behind. And this is mainly due to the high compression ratio of ENMA. So we try to relax it a bit, so to match the others baseline, which either operate in a physical space. And we observe that when we relax this, we have very good performance. And so either better or it matches much lower, better. We do also some uncertainty quantification experiments. So regarding the LMSE, which measures whether outcomes land inside the predicted ranges, we report it against the time. And we observe that as the time evolves, ENMA has lower RMSE, which means that it is a bit overconfident on its first predictions because it relies on ground truth. But as the model will unroll the dynamics and it will digest its own predictions, it is less confident and it produces more diverse results. Regarding CRPS, that measures predictions that are very accurate and appropriately confident, we observe that all the baselines increase in terms of CRPS, but ENMA is the best. So to sum up with ENMA, we propose a method that allows in-context adaptation without quantization. It has also good geometric capabilities and it allows operator learning. However, it still cannot scale to dense mesh points because of the class-notation module, and it's pretty slow at inference compared to fully deterministic approaches. So that's what motivated us to do ECHO, which is the next contribution of the studies. So with ECHO, the context changed a bit. We have now access to new datasets with high resolution datasets, and they are larger. But we believe that current neural operators are not suited for that type of tasks. First, because they are computationally expensive with respect to the number of points in the mesh. They have poor physical preservation under high compression ratios. They accumulate a lot of error for autoregressive neural operators. They are usually task-specific, and most of them are deterministic because generative models are too expensive. So that we try to address some of these problems with ECHO via hierarchical encoder-decoder and full trajectory generation. So what we do on the left is an experiment to show that under different compression ratio, we have good reconstruction capabilities compared to other latent neural operators. And so we observe that our ingredient has lower relative L2, meaning that it is able to preserve much more physics than the other baselines. On the right, we report here how the model accumulates error with respect to time. And we observe again that other baselines that either apply in the physical space or in the latent space or in our generative or deterministic, they accumulate more error than echo. So echo targets complex problems on large meshes, and there's trajectories are potentially long. And what we want to do in particular is multitask generation, meaning that we would like a model that is able to do forward generation. So given two input states, we want a model that is able to generate with full trajectory in one shot. We would like also to do interpolation, for instance. So we give the first initial condition and the last time step, and we like a model that is able to interpolate the missing frames. Or we would like a model that is able to do backward generation. And so this should be done without retraining the model. So what we do first is that we train the encoder-decoder. So the encoder relies on a hierarchical encoder. And then we train the process. And here the process does full trajectory generation via the DIT. Regarding the encoder, it takes as inputs so a set of input states, which is potentially defined on a regular mesh, the corresponding physical coordinates, and the continuous convolution takes as input also a regular query coordinates. And here, this regular query coordinate is not learned, so it is supposed to be fixed and not trained, which allows us to save a lot of compute during training. And we then further compress information via CNN blocks, both in time and in space. So continuous convolution is just a generalized operation of the classical convolution. So it allows continuous evaluation and it allows discretization-free modeling. And so this requires to compute the distance matrix, which can be expensive. So we restrict here to local neighboring to save compute again. Regarding the process, so echo relies on the DIT, as I said, and here the DIT takes as input a trajectory. We will mask some of the latent tokens of the trajectories, so some latent steps, and we randomly noise them such that as inference, the model is able to perform different tasks, such as backward generation or forward generation. Regarding the evaluation, echo is evaluated on 10 different datasets, so 8 2D PDs and 2 3D PDs. And we report 2 different types of experiments. So we compare to different autoregressive methods and regular grids. So again, this is because most of the neural surrogates are defined on such grids. And we also compare to different latent neural operators that directly operate on irregular meshes. Regarding the results, so here we report on the left the performance for the backward task, and on the right the performance on the forward task. And so ENMA is the color is in orange, and the gray one is the best deterministic approach. And so echo is the red one. And we observe that across datasets, echo is on par or better than other baselines, both in the backward task and the forward task. And so what is particularly good with echo is that this model has been can perform both tasks at inference in 0 shots, while other baseline has been trained specifically for each task. We then also report some results on 3D benchmarks. And so what we observe is that across time, echo accumulates less error than 3D problems. Only FNO is performing very well on first step prediction, but we observe that it diverges when we unroll the dynamics further. And what is particularly interesting for us is the ability to generate trajectories fast. And so we report the inference time, so to generate one trajectory compared to other baselines. And we observe that on deterministic approach, in gray, echo is on par with them by generating the trajectory in one shot. And echo is much more faster than the other generative model, which is Armand. Regarding the results on irregular meshes, we report it on 4 datasets, so warped city, eagle, cylinder flow, and shallow water. And we report 2 types of experiments, so 100% input sampling and 20% input sampling. This is the same experiment that I presented in ENMA. And so we observed that echo is on par with all datasets. So those in colors means that echo is better. And we observe, for instance, on the reconstruction capabilities of echo on the vorticity equation, that it can be close to 4 times better than the best baseline. We also do a very important task for us is to observe and to check that echo is able to generate very dense meshes in one shot. So what we do a super resolution problem. So we give as inputs to echo trajectories that are defined on about 20 million points. And we would like a model that is able to generate that type of trajectories on a single H100 GPU. And you observe that all the baselines run out of memory when echo is able to handle this task. So it means that echo is able to support large meshes. It has a pretty low reconstruction error, and it allows to handle complex geometries and domains. So regarding to sum up, echo allows one-shot generation on arbitrary domains. It is pretty fast at inference, and it's scaled to million-point PDs. And it has competitive performance on in-distribution and out-of-distribution results that I did not present here. There are, of course, still some drawbacks, like it struggles to model very high frequencies because of the encoder-decoder module, which usually happens for all models that have an encode process decode framework. And on the right, I wanted to report one generation from echo. So echo is able to generate data via unconditional generation. So it can just generate data. So to sum up with this thesis, I tried to advocate to move towards more scalable, generative, and adaptive neural operators for parametric PDs. So in the first chapter, I tried to show the potential of adaptive conditioning, either via gradient or in context conditioning, and to show that it can boost generalization. Also, then I tried to present a unified framework to do it via ENMA, which allows in-context generation without quantization. It allows to handle arbitrary inputs via operator learning. And finally, I proposed echo to scales to more realistic problems on dense input meshes. There are, of course, some limitations on the results of this thesis. So first, there is a lack of analysis of the generative capabilities of the neural networks. So I've usually done some tests, but usually as additional experiments on top of my results. So that's why we also proposed a work recently where we specifically target PDO forecasting, but for the probabilistic, we focus on probabilistic modeling. And so we proposed a way to learn more calibrated neural surrogates. And another limitation of my thesis is that when back at the times, most of the data sets were not real stochastic and turbulent systems. So we proposed a data set that is turtles, that is a real turbulent 3D system in time with very high dense meshes. And what we do in particular here is that we allow so we trained it. The numerical simulators are generate data on GPUs. So it allows also to compare the speed of a neural surrogate to a real numerical solvers that has been that use good GPUs. Regarding some perspectives and what to do next, one thing I'm very interested in is to move towards generative architectures that directly operate in the physical space, or to be more precise, in a representation space. So a space where you do not compress data. So the goal is to avoid to compress data and to keep all the frequencies we need. Then I believe that type of architectures could be used as a foundation for multi-physics problems. And it would be interesting to see how we could transfer to new physics with that type of approaches. And also generative models usually will need some post-training. So I believe that could be interesting to train as a post-trained stage neural surrogates via verifiable physics rewards to reduce error accumulation and to make sure that the simulations respect some physics. And finally, a very recent trend is steering. So LLMs, they showed some interesting behaviors where they could be steered to a specific task. And I believe that we could do the same for generative methods. And what I believe could be interesting is to apply it to unseen PD regimes via reference examples. So beyond the papers I presented, I have also the chance to work with different PhD students in the lab, which ended up in great collaboration. So I would like to thank them. It was all for me. Thank you for your attention. I'm ready for questions.
J'attends quelques minutes, éventuellement une minute.
Ouais, je pense.
Okay. Thank you, Armand. So we can now start the question time. It is usual to start with the referees. So and particularly with the referees, who is the farthest one from the. So I will ask Gilles to start the session.
Est-ce qu'on m'entend? Tout fonctionne?
Oui, très bien.
Okay. All right. We switch to English, of course. Right. So, well, first of all, congratulations for the excellent work. I read the thesis with real interest, and I think it's really good. And most of all, I'm certain many of the ideas that you have presented in those papers will be important, not only for PDEs and modeling PDEs, but I'm certain also for other applications. So as you have read maybe in my report, I want today to focus our discussion on one thread, which would be the reinterpretation of your work, but from a probabilistic perspective. Because you say in one of the objectives of the thesis at the beginning that you want robustness, but it's not really addressed, in my opinion, very directly. And I think it's a bit of a pity because in the thesis you almost build entirely the machinery that you'd need to have a proper probabilistic modeling of the problems, but it's never fully exploited, in my opinion. So for example, you have a latent variable for the environment, you have a generative model over the trajectories, you have a prior condition observations, but mostly when you evaluate the results, except for a few plots, and I'm glad that you have presented a couple of them today, you focus on metrics that will that would evaluate the quality of point estimates, which is quite different from properly assessing the probability distribution. So my first question will be about JEPS in chapter 4. And it will be a very simple question. So when you adapt to a new environment, can you tell us what kind of estimate of that environment are you exactly computing?
Could you repeat this? So you mean what is the context capturing?
So when you run your procedure for adaptation, you minimize some loss, but I want you to try to express at the end the solution that you find. What kind of estimate of the environment are you exactly computing? It's only implicit, but I would be curious to see if you understand exactly what that actually corresponds to.
When we train our models, when we try to adapt to an environment, what we like is that the context captures the environment specific information. So what we hope is that the context captures the PDE parameters. So we train it via classical loss, that is like a relativity loss. But what we hope for is that just by doing the task that we want, so next time step prediction, the context is able to capture the environment specific that allows it to adapt to a new system. And so in prior works, we showed that this context actually captures the PDE parameters. So we are able to infer the PDE parameters from this context.
But would you expect any uncertainty attached with this solution, with this context that you retrieve?
So we did not focus in this first contribution. We did not really focus on uncertainty. This was not the target of the contribution. So we just wanted the model that's able to generalize to new systems. But I agree that what we could do instead is that we could have used an encoder, for instance, VIE, that takes as input the trajectory, and we could then try to capture the environment specific information. So it outputs the encoded, the latent context. And so we could then sample multiple contexts to see the uncertainty of this with respect to the environment. So, but here the environments are pretty deterministic. So the PDE knowledge is embedded into this context.
No, the PDE is deterministic, but still, I think if you were to change the trajectory, even though if it was still generated for the same system, would you expect to retrieve exactly the same solution? So you would
No, I guess that we would like some form of uncertainty and also the context. So yeah, one direction would be to learn it in such that you could sample multiple contexts and see if like exists. So in average, we could capture like the same PDE information.
because so what I wanted maybe to realize is that from my perspective, it's as if when you minimize the the squared error, it's as if you are implicitly assuming a Gaussian likelihood, and then you just retrieve a best fit. So you are just computing a point estimate, in this case the maximum likelihood estimate, and that's it. Although behind actually there is a classical posterior inference problem, and you are just building an approximation of that. And so if you had approached the problem from that perspective, you would have satisfied from the beginning the robustness approach, the robustness, sorry, objective of your team.
Yeah, I agree that that was not the target on Jeff's, to be honest, but yeah, if we would like to increase and improve robustness, that would be a very interesting approach.
Okay, my second question is about Zebra. So in Zebra, one of the strengths is that you can produce many plausible trajectories as a distribution because you can sample these tokens. But if I read your results correctly, all the tables that you show, what you actually score and measure is the quality of a low temperature sample.
Yes,
And you compare that to the truth. So
yes.
at
Because
the
we try to compare to other deterministic approaches. So here the goal was not to assess the ability of Zebra to generate multiple plausible predictions, but instead we wanted to see that if we take the mean, we're able to have scores that match other approaches.
But so if that is the goal, why do you need a generative model at all?
Yeah, so the goal of Zebra was just to, so we observed that there are some trends in LLMs, so they're able to do in context learning. and we wanted to take the same approach. So we trained a model with the same architecture, same loss, and see if we are able to get the same type of behavior, which is in context learning. So the goal was just to see if in context learning actually works for PDs. So that was the motivation of the paper. But we did some tests, so they can maybe show. So here we computed the temperature as a function, and so we reported different loss with respect to the temperature, and we observed that as the temperature increased, of course, the rollout loss also increased, but we have also better CRPS and confidence level when we increase the temperature, meaning that the model generates more plausible trajectories, and at least it covers a larger confidence interval.
Mhm. Okay.
But yes, this was not the focus of the paper, and we at that time we didn't really focus on the uncertainty quantifications ability of Zidor.
Okay. And then I have two other questions on echo in the last chapter. I will skip the chapter on ENMA because I think it's very strong and I don't have any comments, so it's well done, and I will focus on this one instead. Yeah, so there I actually have a similar question. So echo is a generative model that you train with flow matching, but again, what is the generative formulation really doing here for you? So is it there to give you a distribution over the trajectories, or is it mainly to keep the samples sharp and on the data manifold?
There are different desired properties of generative models. So first, of course, they can generate multiple plausible solutions. So that's what I did some tests on uncertainty quantification, but as an additional task. But what's also important for us is the ability of the model to preserve high frequencies. And we believe that operating in such a space, so with the generative model, allows us to better retrieve some frequencies, because generative models do somehow some form of auto-regression into the frequency space. So that was also the motivation of the paper. So that's one of the limitations is that I couldn't test my model on real stochastic datasets, but the purpose of generative models is to allow to handle that type of problems where you would like to have distribution of trajectories.
Okay, so that's what I thought. So, but that's fine. So do I interpret correctly that you use a generative model basically as some kind of regularizer to give you good predictions instead of just going for the MSE? And, okay. Then I was also quite interested in this chapter because it's very close to some of the work we are doing. So you have a generative model of trajectories. You have parts of these trajectories which are observed, and you want to generate the rest. And that is exactly the structure of another problem which we call data assimilation in other fields, and specifically in oceans and weather science, and you cited some of those in your introduction. But where in addition to that setting, you have actually noisy observations. You don't observe exactly the parts of the trajectories. You get, you have noise. It could be nonlinear interaction of the states. You don't observe all the variables, so it's a huge mess. So could you see extensions of echo that would be able to handle observations that you can relate probabilistically to the trajectories that you are generating?
Yes, I believe this is like very similar works. So I saw your comments in the, so I checked the papers and I feel like there are very strong connections. And yeah, I believe that, so one idea of echo was also the ability of the model to handle noise inputs. And so, yes, there's our clearly next extensive experiments that we could do to see that the echo is able to digest also noise inputs. So we did some tests in partially observed data. So it's a way to get some noise representation. But another way is just to inject noise in the model input, like the data.
But how would you, I'm a bit curious, like implementation-wise, how would you, because so far you have tokens and the transformer just see these tokens and generate tokens because that's the only thing it knows about. But now these tokens, which represent parts of the, if I'm not mistaken, part of the trajectory, if they are noisy, how do you specify the noise exactly?
You mean you mean in the generative process or as input?
Yes, as input.
So I think the classical experiments could be just to inject different type of noise and just see how to just inject noise into your input. Or there are now data sets actually that are real experiments with noise included. So it could be interesting to do some tests on numerical simulations. So we train a model on the real on the numerical simulations, and you do tests on real world data with noise. So that's the type of experiments that we try to do. But the gap between the two datasets were too high, so ECHO was not able to handle that type of problem. But that's the typical case we could expect a generative model to handle.
Okay, okay, thank you. And I had a last question because your approach is also interesting in the sense that you generate the trajectory all at once. If I understand correctly, you don't go for another regressive scheme.
That's not exactly true. Actually, depending on the length of the trajectory, we will learn so subsequences if needed, and we then just train it as a. So we do autoregressive modeling, but we generate parts of trajectories.
Okay.
To how long the trajectory is. So for instance, the Gray-Scott equation, I think there was 160 time steps to generate, so it was a bit too high. So we were generating 40 time steps per forward.
Okay, I see. No, but that makes sense. But my comment was not exactly on that anyway. It was about the scalability. So this was also in one of the summary points of that work. You said that it scales to 1 million data points. I think that's how you call it. So do you think it would scale to like an actual weather model where it would require 2 or 3 more orders of magnitude? So typically to represent a state at one time step, you would have a grid at 0.25 degree resolution, which would be 1000 by 1000 more or less, or something like this. And then you would have several levels in altitude, typically 13 or 37. And then you would have several physical variables per point of that mesh. And then you want to generate hourly or hourly time steps, but over, I don't know, 1 week or 2 weeks. That would be the horizon. So you are quickly in the order of 10 to the 9 or 10 to the 10 variables in total to generate. Do you think that would scale to this regime?
That's a good question. So I think that if I'm correct in weather, they do not really need to handle irregular meshes because they usually just put the map on the plane, and so they do not need that type of problems to handle. So do not need this continuous compilation operation, for instance, which is the expensive part of the encoder. So if we get rid of that, so all the compute, all the bottleneck will be at the trajectory level of the transformer. So I guess that it could work somehow. The question is that whether people in weather really care about generating multiple time steps in one shot, because I think most of them just employ them as autoregressive models and they just use one time steps and they generate everything autoregressively. So I think in terms of computation, it should be okay. I mean, you can compress information as much as you want. So it really depends on how much physical information you want to keep. But I'm not sure if the people in weather.
I think they would not be interested, of course, for forecasting applications, but for reanalysis, if you want to reanalyze past weather, there you need to condition over entire histories of observations. So when you generate a time step, you want to account for what has happened after that, which you already know because you are reanalyzing past data. And that you can do easily autorecursively. So
Yes.
there it would make sense.
Yeah, so yeah, I guess that type of architecture will definitely make sense for them.
Okay. Thank you very much and congratulations again.
Okay, we can now move to the second reviewer. Maybe you have the mic. Yeah.
Hello, can you hear me? Hello? Yes, so first I want to congratulate you. We think it's really a very nice piece of work in this area of scientific machine learning. And you had a really nice progression. People. So can you return? But this also brings me to my first criticism that I put in my report, so we not survived. He really had an opportunity to tell a nice story from your different contributions. Whereas, well, okay, you just read it in your papers. Yeah, I can understand why it would be quite some work to write, but sometimes it gets really, let's say, it's annoying when really no enjoy reading the whole lot, but yes, I think we have done better transitions and the reference little chapters, not really obvious little chapter 6 and 7, let's say. Or sometimes when you don't even have James as a background for the war or something like that. That made it much stronger body of work.
Yeah.
But okay, anyway, the work is there, the work is nice. My second, let's say, global comment, again, I was in my report, is about the link with the PD world, involving like math and the simulations. So the motivation is to help them or to do better, or it's one way or the other. But you don't refer to any of these words in your work. And this is a pity, especially this is something that could be really necessary when you want to compare. If you compare machine learning approaches between, and you show that you improve over the state of the art, that's really fine. But you never compare to any other method, or you never question the way you compare. Because you compare MSP, compared to a solution given by simulation. What does it really mean? When you get 10 to the minus 1 and 10 to the minus 2, whereas people in the PDE world go to ratio of 10 to minus 8, 9, 10, or even worse, or smaller. So at which point is it interesting for them? Because it might cost a lot more, but they get to a much better precision. Or put it the other way, what would be the cost of the approximation to the type of level of error that you obtain here? So maybe it's not that large, so maybe you don't gain that much. What can you say?
So I agree with you on that point. The point is that I think what we're trying to do in the lab is not to show that ML models are right now better than PDA models, because we know it's not the case. So what we are trying to solve is just to see if the ML models are able to learn some physics. So we already know that we could learn, like we could train, we could get a numerical solver that is much more faster and produce much more better results than a neural network. But that was not the goal of this thesis. So this thesis tries to just address new methods that tries to show that we are able to learn some physics somehow.
Yes, but you did not really answer my question.
So
because yes, I agree, okay, but you also cite as a motivation that the PDE approach, the standard approach, is far too costly.
Yeah.
But you don't give any hint.
Oh, yeah. So on that, what I could
be the case.
Yeah. What can I say on that is that so most numerical solvers that we use to evaluate the models are numerical solvers that we used ourselves, so we generate our own numerical solvers. And we are not experts in physics. So what we try to do as an extension here, that's why I presented this work, is to propose a real system, so a real numerical solvers that is trained or that is using GPUs. So to clearly assess the benefits of neural circuits against numerical solvers, because most numerical solvers are defined on CPUs. So I think that a neural circuit could be much more faster than a numerical solvers that is defined on CPU. But if we use like similar constraints with similar compute, I think the question is much more hard to answer. So that was also one motivation of this. Yeah. And that's why I say it as first.
Okay, thank you. Now maybe about the zebra. Yes, you had in the last page of the zebra chapter, you say, well, we are also able to predict the whole trajectory and the token by token. We get a 10 times increase generation.
In Zebra.
Zebra.
So could you repeat?
Mention it here.
Oh, in my thesis?
Yes.
So could you repeat the question?
You say you developed Zebra, you compare with the graph,
Yeah.
then we said, also we were able to predict the whole trajectory and not only token by token.
What we did in Zebra is that we also used we use the Zebra as a conditioning, to condition a unit that is much more faster to increase speed. So that's what we did also. Yes. So we didn't include it in the results because the motivation of Zebra is just to understand, to show if so are we able to do in-context learning with neural networks for PDU modeling. And so we then did some extensive experiments to show that we could also increase speed if needed because Zebra is very slow. And so what we did is that we used Zebra as a way to generate one token that captures the context and is used as an input to the unit to generate the rest of the frames. And so this allows to go much more faster than Zebra, which is very slow. So it was to address another criticism, which is the speed. But the main goal of Zebra is just to show the potential of LLMs to doing context learning for PDs.
And why didn't you continue on the LLM?
Because we believe that quantization is not really meaningful physical systems. We already discretize trajectories to get solutions. So quantization would mean to discretize the space, which we believe is not very meaningful. So that's why we proposed ENMA. So ENMA is the same strategy where we try to generate tokens one by one. So it has the same spirit than LLMs. But the whole point here is that we do not quantize space anymore, and we can operate in a continuous space. So meaning that the model is able to generate any outputs. So it is not restricted to the code.
So switching to EMMA, you write and the results show that it's not that successful compared to state of the art, including Zebra.
Yeah, so it really depends on the data sets. So on the three first problems, it's better. But indeed, on the two other data sets, which are wave and vorticity, Zebra is sometimes performing better, or sometimes it's the FNO. But so that's what I said, is that we also relaxed a bit the compression ratio, which was too high. For instance, FNO works in the physical space directly, meaning that you do not compress information. While with ENMA, we had to compress informations to get, so we go into a latent space. And so if we compress less on wave, we are more better than over baselines. We are 50% better in distribution and 10% better out of distribution. And only on vorticity, we are still a bit lower, but it's much more closer than over baseline. So on 4 data sets, we're better. Or we are second best.
What about the CPU cost or more people?
The cost in inference speed?
Cost.
Yeah, so that's one criticism we can have for ENMA. I don't know if I plotted the results here. I can check.
Yes, later.
So here I report the results on Echo. So I compare the inference time of ENMA compared to other baseline. So we observe that NMAP takes much more time to generate one trajectory because it generates tokens one by one, and it has to solve for each token an ODE, which is expensive. So that's why we try to propose Echo to do full trajectory generation.
Also, we have when you use it for number of function, even the beginning of the trajectory.
Yeah.
What is the importance of the number of steps you give?
Yeah, I did not report the results in the presentation, but we did some ablations to see how it impacts. And usually the higher, like the bigger the input sequence you give, the better the performance.
So we can expect, but
Yeah.
how much that is.
So starting from 3, the model starts to be very good. And then it is much more slower. The performance are increased, but much more slower.
Okay. And when you are there, about Echo, because it's a bit study of this, whether you do 0 shot, 1 shot, few shot only. You say you can do 0 shot, but you presented results with 1 shot.
Yeah, sorry, yeah.
Sure.
So maybe it is a bit misleading. So in Echo, we did 2 different types of experiments. So when I talk about 0 shots, it's the ability of Echo to handle different tasks. So here you can both do backward, forward, and interpolation tasks in 0 shot. So it does not need to be retrained. And we then wanted to do some out of distribution generalization results. They are there. And so what we did is we did 2 types of experiments. So one is long range generation. So the model has been trained on until T, and we try to extrapolate. And so this is the qualitative result. So we observe that it still preserves some good statistics, but some high frequencies are missing. And so here is the few shot that you probably saw. And so we did some tests. So so we wanted to generate 2 new PG parameters. And so we did some tests in 0 shots. So the model at inference, and then with some few shots learning. So we give to the model about 10 trajectories and is retrained for like 5 epochs. And the model is able to match the performance similarly that what he saw in distribution. And so this is a forward problem here.
Okay. Thank you very much.
Thank you.
Thank you. And now the other members of the committee, and I would ask Professor Lulu to ask his questions.
Sure. Can you hear me?
Yes.
Yes.
Okay, good. Nice. Yeah, it's a really nice presentation and great job. I have some questions from some technical questions and some high-level questions. Maybe I can start with some small questions on technical side. In the first part of gap part, where you say you can go from one environment or one condition to another, and you showed I'm not remember which page, and you showed the accuracy of different environments. Some are good, some are slightly worse. To do it for I'm not sure if you go next. Yeah. For example, here.
Yeah.
I go to different cases, Burgers, Gray Scott, Comgrove. So you can see some errors, some are large errors, some are small error. So what's the reason for this? For example, is this kind of similarities between different data sets? If they are more similar, then it would be easier. If they are different, it would be harder. What do you think?
So is your question about the relative L2 metric or like the comparison between the other baseline? So how much the model is better than the
Just
baseline?
the error L2 relative error.
Yeah, so for instance, on the pendulum and Kolmogorov, like the datasets are much more complex. So that was a bit surprising for us, but like the ODE, so pendulum ODE, is a very complex ODE to solve because we did some experiments with where new environments were corresponding to chaotic behaviors, and so the model was trained on very simpler environments, and when generalizing to chaotic environments, it was failing a lot. So that's why the model is having lower performance on out of distribution environments, for instance, with respect to other baselines in terms of relative L2. And similarly for Kolmogorov, we have also very bad relative L2 because the out of distribution environments are very complex. So what we change here is for instance, the viscosity, but also the domain of the solution. So we were training on one domain and we wanted to adapt to a new domain size. So these are very complex environments. First, compared to other data sets such as Gray, Scott, or Burgers, where only like the viscosity or the PD parameters were changing.
Okay, I see. For the next part of the in-context learning, I just want to clarify one point. Why I say the training. For the Zebra case, basically, do you train a single PD each time or multiple PDs simultaneously for the network? What's
So
how to do the training data set? Yeah.
what is in the training data set?
Yes. For example, you have many PDs, right? Each time, do you only train one PD or you train many PDs simultaneously?
It's only one PD, so this is one physical system, but in one data set, they can have different environments. So here, I report the number of environments. So for all the data sets, we have about 1,200 environments. And here, an environment corresponds to a different PD instance. So meaning the diffusion or forcing function can change, the advection speed can change for the advection equation. So that's what is changing from two environments. So
Okay,
in
but ideally, yes, I see. Okay. Yeah, but you could also train all these PDs simultaneously, right? You put all the PD together for the training. It's learning. So ideally, we hope the network can also identify the PD and do the prediction for many PDs. Have you tried that?
Yeah, I agree. So that's something that we would like to do next. So that's what I believe differentiated my work, so which is parametric PD problems with multiphysics problems. And so we are actually working on a work where we try to pre-train a model on multiphysics with a GPA objective. And so in this type of work, we have multiphysics. And what we expect is that the model is able to digest all this physics and could adapt to a new physical systems as inference. So this is different work here, but I believe that that type of architecture could, of course, be the foundation of multiphysics problems.
Okay, good. Then if we go to page 55, sorry, 53. Uh, yes. So here for reconstruction, I want to clarify, it is when I do reconstruction, the data is clean or is noisy?
Okay, so here we report three different types of experiments. So we change the input sampling. So there's the 100 input sampling, 50% input sampling, and 20%. So the data is clean, but the number of points in the mesh can vary. So in the 20% case, it means that 20% of the input points are given to the model, and the model must predict all the points. So it must retrieve the 100% grid. So the data stays clean, but it must so it's a partially observed problem. And so we report the results because the model compress information. So what we would expect is that the model is able to also reconstruct everything, but it's sometimes not possible as you compress a lot. So we want to preserve as much information as possible.
Yes. Have you tried, you add, let's say, some noise into data, then do the reconstruction? For example, you take 20% of data, but also you add noise. Have you tried this?
We did not try this, but yeah, I believe this is an interesting direction to see if like the model is robust to noise. So more than like just removing inputs, also like noise the inputs. It could be very interesting to test indeed.
Okay, that's fine. Then can you go to 55, page 55 into page
75?
Yes. Uh, uh, oh, right. So here is when you say UQ, what's your metric for UQ? Uh,
Um, so here what we sample a lot of, so we train models, generative models, and we sample 10 trajectories from each model, and we report the performance of the models, so with respect to time. And so what we compute is the RMSCE and the CRPS. So those both metrics are UQ metrics that assess if the model has good confidence interval or the prediction are accurate.
okay, I see. That's good. Um, let's see. Okay, then can you go to page 69? Okay, good. In this page, so echo is better than other methods, other baselines. But if you look at the L2 relative error, in many cases, it is still large. For example, for backward task, the really Bernard equation is 11%, active matter is 17%. Even for forward task, active matter like 28%. This is still large error.
Yes. So on altimeter and acoustic ASM, so these are datasets from the web which have much more complex physics, and all baselines are pretty bad at inference. So on next time step prediction or fuse time step prediction, they are relatively low error. But as you accumulate error, the model starts to really diverge in performance. So here we report the relative L2 average time steps. So that's why because we also do some long horizon generation, they have sometimes bad performance.
Okay. This includes error for long-term prediction. Okay, that makes sense. Um, now, okay, can go to page 74. Okay, good. In this page, you show this unconditional generation by echo in the movie. So my question is, for this Kolmogorov flow, right? If we compute, uh, uh, if we put this generated field back into the PDE, would it satisfy PDE, which means is the physically really correct in the PDE sense? For example, would the PDE residual to be equal to close to zero?
Could you repeat? So you generate one data with echo, you want to give it back as input to the model?
No. So here you generate solution, right? You generate this
Yes.
snapshots and trajectories. Then we put this solution or this PDE data back into the PDE equation with the divergence.
So you mean
Like
you,
also
gen- so you mean you give it the numerical solver, just the initial condition, and you generate the trajectory, for instance?
not exactly. Let's say in a simple case, but if we compute or if we have the velocity in the u and v direction or x and y direction, then we know if we compute the divergence of the velocity, it should be zero, right? Divergence free.
Yeah.
Would this generated video satisfy this property?
We did not check, but so we observed when generating. So I believe that it would maybe work for like the first time steps, but as the error accumulates, we observed when so in this generation that some like frequencies are missing, meaning that as it goes out of range generation, echo is not able to preserve all the statistics. So I believe that it does not respect all the physics up to some point.
Okay. Um, oh yes, then they can go to page 76. Yeah, in 2 pages. Yeah, here. So I think you mentioned for the second point here of the new benchmark, you mentioned you have some GPU solver over traditional solver, and you mentioned that you had some comparison in this paper to compare speed. Can you can you go to some details of how is comparison? How is the speed if we compare machine learning versus advanced GPU code for traditional solver?
Yes, so I think like the gap is not that larger that we believe. So to generate the data here, it takes up to 20 to 30 minutes, I think, depending on the case. While for neural surrogates, as the number of mesh points is very large, you have to do some form of tiling and you compute solution region by region. So also neural networks are very expensive for that type of problem. So when I did some tests, it could take up to like 15 minutes to generate one solution with the neural network, because classical neural operators are not able to handle that type of meshes. So here, the number of points for each mesh can be between 3 million to 9 million points, which is huge. And so many of the neural surrogates right now operate on the million point scale, but not larger. So that's clearly a bottleneck of neural surrogates right now. And moreover, like the data is super stochastic, so neural surrogates are not even able to actually learn something meaningful right now because the stochasticity is like too hard to capture.
I see. Okay, good. And you mentioned, right? You mentioned the dense points in your slides and your answer. I think this is something probably we should consider carefully. So in traditional solver, the reason we go to a dense mesh because we know the error has a convergence, let's say second order convergence, right? The error is proportional to delta x to the square. However, for machine learning, it might be different, which meaning, let's say in many cases, we have a machine learning solver, let's say surrogate solver, let's say operator learning, neural operators, or diffusion model. Let's say we achieve 1% error, let's say in 1 million points. However, even if we increase from 1 million points to 10 million points, the error not necessarily go down because now the error is not dominated by the number of points, it's dominated by the machine learning method itself. So I think so whether it's really necessary to go to really super dense points for machine learning is it's not clear because adding more points not necessarily make the performance better because that's not the dominant factor. What do you think?
Yeah, I agree. I believe that we need to capture up to some point to certain number of input mesh. So we should still have neural networks that can digest certain number of input points. But there are like some problems where in CFD, for instance, they require like hundreds of millions of points. And I believe that for that type of problems, this makes maybe less sense for like neural surrogates to operate on very dense meshes. And that's also why I believe that we would need some neural networks that can learn in the representation space that do not compress that much information. So what I believe is that physicists give us to us data sets that they would like us to work on, meaning that they can generate solutions on very dense mesh and then they subsample it and say, okay, what we want from you is to make it work from these mesh points, from this mesh. So what we are given by physicists, we should not further compress it. That's my hypothesis.
Okay, good. Let me see. Okay, I have a couple other questions. So one question is, in your papers, you did a lot on the let's say points in the spatial domain. However, in all cases, in the time domain, it's always uniform snapshots. So what do you think of but in many cases, if we consider traditional solver, now the traditional solver basically in many cases, right, people always do some kind of adaptive time stepping method, especially for some steep problem or complex problems. So how can we incorporate this idea into machine learning?
Yeah, I believe this is not that hard because there are already some works that try to address this type of problem. So the classical way to do it is injecting as conditioning the discrete time used. So as we can get it from the neural solvers, we can also give it to the neural network as input. And for transformers, we can also inject it via like some form of positional encoding. So we could inform the network. So what are like the time steps between, like what is the discrete time into two time steps? So we could just learn it. So we could inject this information as positional encodings for transformers in this sense. But there are various ways to do it. So we could inject it in the adaptive layer norms or give it as in context inputs. There are different ways to do it.
Okay, good. Maybe then my last question. The last one is about let's go back to geometry. Have you tried a data set with different geometries in different environments? For example, in different data points, the geometry is different.
No, we didn't work on different geometries like per environments. The only things that we changed is the domain. So on the Kolmogorov, we changed the domain size, but we did not work on like different type of geometry. But
Okay.
it's a very natural. So we could also define an environment as a like physical simulations defined on one geometry and a new environment correspond to another geometry. And we like a model that can then adapt to a new environment corresponding to the new geometry. This is this makes sense.
Okay, good. Great. I don't have further questions.
Thank you.
Thank you very much. So I think that now it's my turn as an examinator. So thank you for the presentation. It was very dense, but also very clear with the general lines, with the details and tricky, of course. And it makes me a lot of connections with computational fluid dynamics. And so I have some questions, maybe first of all, some general ones. So maybe starting with the discussion we just had with Professor Gibbon. Well, we were talking about the need to move toward these large-scale problems with dense grids and high stochasticity of the problem, even if it's not stochastic, actually, it's velocity, but it's stochastic. But anyway, for sure, when you want to do some high-fidelity simulations of fluid mechanics, you do need those grids because the problem is hugely multi-scale, and if you don't resolve all the scales, or you are missing some of the physics. You are missing the contribution of the smaller scales on the transport of mass, energy, and so on. But in practice, for very high Reynolds number problems you encounter in engineering, it will in practice not be possible to resolve all the scales. So the typical solution, which is used in mechanics, is to use a closure, which means that you will solve up to a given scale, which will be determined by your level of fidelity you want to achieve, and also the kind of information you care about. And then you will, model whatever is left. So I was wondering if a similar approach could be used actually in neural operators, because right now you are trying to learn sort of brute force approach all the scales simultaneously. But in practice, what you would maybe try to do is to separate the mean contribution, which is smooth, so probably much easier to learn for your neural operator, and then separate the contribution of some of the scales. You will never be able to, to capture all the scales. Imagine that you have a flow around the boat. The Reynolds number will 10 to the power 8. So nobody is never going to capture all the scales up to the Kolmogorov scale in your case. But you don't care. Provided that you capture correctly the mean flow and some of the larger scale, which are those who are going to affect the stability and the drag on your boat, you don't care about the other ones, those small details. So yeah, maybe have you got an idea of how we can implement scale separation in machine learning methods and eventually learn neural closures for truncated model. That is, you introduce a truncation to neural representation, you only represent some range of the scales, and then you try to model the other ones by learning the question. So it's something like that is possible.
Yeah, so I did not try that in my thesis. So what I did try is like for in JEFS, what we tried, for instance, is that, so for the Komogora flow, we were computing it, so the LES formulation. And so we tried to complete the physics model with data-driven model. So we wanted to uncover the missing term from the LES simulation. But I believe that what we could do is we should have as inputs the LES data set, for instance. So, and we could first train the model that is trained on the LES. But what we like is to, from this LES to, so you would like the neural network that is able to directly model the.
Yeah, for instance, instead of using the snapshots as they are, you could take an average of the snapshots. This will give you the average flow behavior. And you first learn that one, okay? And then you try to extract from snapshots the spectral content, that is the higher, the smaller scales. And you model them separate. And then you try to reconstruct both of them. This is something which is used in what is called synthetic turbulence. That is, you have some mean flow, which could be analytical or something, and then you try to inject turbulent fluctuations, which are artificial, but they are, for instance, drawn from a spectrum of scales, which is close to the physical spectrum. Really, isotropic or homogeneous isotropic turbulent spectrum or something else, or a learned spectrum. I don't know, something like that. So I don't know if it's something.
Yeah, I believe that we should the model should output like an average formulation.
Exactly.
And then
on
top of that, you train a neural network that tries to, that takes as input this average formulation and tries to predict the rest. So I guess that we could do it, but this requires two different networks that are trained very separately.
Probably. And which, take into probably, I don't know, we could maybe imagine, a small scale network which takes as an input average and then adds the fluctuations.
Yeah, I think this is doable, but we should definitely need like either one network with two different branches, for instance, or two different networks that are trained like on two different objectives.
Yeah, or something. Yeah, okay. So the other point is about the model which are trying to capture a wide range of physical problems. So, mechanical engineering point of view, you can ask, where do you want to do that? Because a fluid mechanics is not going to do solid mechanics one day and fluid mechanics the other day. So I was wondering if this is more related to have a sort of equivalent of large language models where you can interrogate them today on high energy physics and tomorrow on, I don't know, Greek philosophy, and they still have an answer. So I understand the idea, but the problem is that in physics, well, even if you have some examples of, for instance, in the well benchmark you consider, you have some examples of varied physics, but it's still toy problems. And as you said, when you just focus on one of the fields, so incompressible Navier-Stokes, well, you already struggle at representing all the wealth of physical phenomena you could have only in Navier-Stokes, in incompressible Navier-Stokes. And the problem also there is that you are currently lacking data, because, well, of course, LLM were trained on plenty of information about high energy physics or Greek philosophy available on the web, which is not the case in a physical problem. So how would you tackle that? Do you think it's realistic to go where those models will it ever be possible to do that? So
I'm not sure, but I'll try to address it. So I think like what people hope right now is that because we, as you said, we lack of data, so we usually have some data sets defined on each specific problem. And if we need a lot of data on one problem, then we need much more data, and this requires simulation. So what people want to do is to learn from different physical systems, because some of the physical systems share still some PDE coordinates. So some terms in the PDE can be can be seen in another physical systems. And so what people hope is that because neural networks are very good distribution learner, so you give a huge distribution to your model, and you hope that the neural network is able to learn that distribution, in the hope that if there is a new physical system, you can, given low amount of data, adapt to a new system. So it really depends on how expressive is the model. So that's why people want to now get neural networks that have billions of parameters. So that's what people from Polymatic are doing. For instance, they try to scale their models in a way that you can target all the complexity of the distribution. But I don't think that we will be able to generalize to new systems just without without retraining. And that's
which is what you propose.
You have to inject some sort of adaptive conditioning mechanism, either via fine-tuning as people do information models, or with some strategies, such as having some form of environment. So here, what I propose for parametric PDE problems with environments could be imagined for multi-physics problems. So an environment could be one physics, and another environment could be another physics.
Maybe the last question, which is a little bit more theoretical. I come from computational mechanics. In computational mechanics, when you consider a discretized equation, you look at three properties which are intertrinity. One of them is consistency, which means that you refine more and more your discretization. The discretized equation should tend toward the exact. So the solution of the discretized equation should tend toward the solution of the exact equation, which is something which is not guaranteed for developers, right? Then you have a second condition, which is stability. Stability says that when you compute the error at step n+1, it will be always equal or smaller than error at time step n, which is it is called Neumann stability analysis. And then you have a theorem, which is a fundamental theorem in computational mechanics. It's called the Lux theorem, which says that if you have consistency and stability, then you have convergence, which means that consistency, actually, the first one was convergence. Consistency means that the truncation error of your approximation tends to zero when you refine the mesh, plus stability, your error decreases in time, implies convergence, that is, the solution of the discretized equation tends to the exact solution. And any two of these conditions imply the third one, okay? Which is not the case for a neural operator. So I'm not sure you can have a notion equivalent to consistency in neural operators. Maybe you have your own ideas, I would like to hear from you. But probably it is possible to ensure a training, a notion which is similar to stability, in the sense that when you train, you can compute the errors and then you try to constrain your model to have a decreasing error, to control the error while we iterate with your model. I am not sure, so but I would like to read some here.
So what you like is that by increasing, like if we increase the discrete time, we should have some form of a rule that allows to know.
It's a mathematical property, because in computational mechanics, it happens that the numerical error follows the same discretization as the solution. Okay, so you can rely on that to compute the amplification factor of the error and ask that this amplification factor is less equal to 1. Which means that your error stays controlled. But a numerical scheme, so a numerical discretization which satisfies this property, which is not the case for any numerical discretization, is said to be stable. Okay, and stability is one of the pillars with consistency of convergence. So the fact that you are right, that you are sure that if you refine enough, you will get the exact solution at some point. There's something very close with the exact solution at some point. And
I believe that if we are in the same constraints than the people from the PD world, that should be doable. But as we usually subsample a lot to the grids, both in time and space, because we want to learn operators that are fast. These are I think we do some sort of approximations that do not preserve that type of properties. So a way to test it would be to first train an ODE, I guess, that have this numerical scan, and maybe we could just
So
see.
you would tackle that in terms of amount of data, because in my view, the equivalent of what we are doing when we refine the numerical discretization with the neural network is the number of degrees of freedom. And your number of degrees of freedom is the number of parameters. In our case, the degrees of freedom are the solution at the grid points. In your case, it is the parameters. It's not in your grid. So, and of course, this parameter need to be informed by something. So it is. I know that some people, for instance, Siddhartha Mishra, the was citing there, was trying to find some scaling laws, so that given, I don't know, the Reynolds number of some flow, we can estimate the order of magnitude of parameters you will need to capture all the scales in the field. Because we did some capacity to represent a given range of scales. So I'm not sure if you.
Yeah,
It's very open question. So I don't
I'm
have
not
the
sure.
answer.
I do not have either, but yeah, I guess this is not only a problem of number of parameters. So it's all depend on like on the data you give it to the model.
Sure, but if you have three
Yes.
data and 2 million.
Yeah, but also in terms of like the mesh. I mean, yes, you should have the same properties if you work with the same conditions than PDs. So then the degrees of freedom of the numerical solver should be. I guess there are some similar properties for neural networks.
Yeah.
But I'm not sure.
Okay, thank you. Okay, so thank you very much. I think we are done with the examinator. So I'm now going to give the mic to the supervisors.
Thank you. Well, yeah, I first met you when you were working in my office back in the days, the side of the campus. And from the very beginning, you quickly became involved and demonstrated great technical skills by working with Ray on Coral. And then you brought your own ideas, contributing to the Zebra paper, while almost at the same time, earlier, publishing an excellent paper with Jebs at Neurips. So after moving to Pyramid, I saw you took an important role in the team. You welcome new PhD student, help ensure the continuity of the group, and become one of the pillars, and continue to pursue research with great creativity and energy. So what I could say, not much, but I learned a great deal by following your work, and I could even say that I learned more from you, so you learned from me, let's say. So thank you a lot for this, and again, like all the members of the jury, I want to congratulate you on this great success.
Okay, thank you. Okay, so I will add some comments to the ones that I've touched on, but more or less the same comments. So first of all, I would like to congratulate you for the great of your work. And well, it has been a real pleasure to see you during these years. Okay. And as later on, I would like to thank you for your dedication to your work. So you work very hard during these years. Sometimes after horrible times, not and well, also well, I like very much your enthusiasm and your happiness to discuss research. And well, you came with some different ideas, different initiatives. And you worked with a whole team, well, very positive values. So thank you for that, and so thank you for your commitment and your involvement in the guidance of your PhD.
I think that if there are no PhDs alone who wish to ask a question, No? Okay, so we can consider that the examination session is closed and the committee is going to elsewhere to deliberate. So in your office.
Yeah.
Yeah.
Yes. For Gilles and for you, we have a short discussion now, because that's something like 15 or 20 minutes, okay? Instead of all the business. And we will, so we leave for us, we leave the row of the defense, okay? And we meet on the new link at 20 minutes. Okay, so you should have received a new link. I know if for the vision for vision, just give us 5 minutes just to change mode.
Okay.
Okay.
Ouais, tout de suite.
Okay.
Je vois Patrick, mais j'entends pas. C'est mute. Ah, voilà.
Et Tom? Okay.
Ouais, je t'entends.
Just wait for Armand, he will come soon. Okay.
La page de site, donc ça, c'est les Vous pouvez le mettre en mode gris, on est les deux.
C'est comment on fait?
Tellement de différence entre les deux.
Peut-être.
Quelqu'un prend une photo, c'est bien qu'il y ait les deux.
Toi, tu sais comment on a une grille? Genre pour qu'il y ait les, pour qu'il y ait lu et
Pour qu'il y ait tout le monde.
pour qu'il y ait tout le monde dessus, je sais pas quoi. Tiens, on peut arrêter de partager le truc. On s'en fout.
Affiché. Alors, affiché.
C'est pas grave. Sinon, c'est pas grave. On est affiché, ça.
Ouais, les participants.
Ah, mais
C'est pas bon.
Fenêtre.
Fenêtre aussi, non, fenêtre.
Ah,
Non, ça.
regarde. Bon, écoute, c'est bon comme ça, quoi.
Stéphane,
j'aime pas vu ça.
Et c'est dans quel sens? C'est d'abord lui, c'est après toi?
Non, c'est d'abord moi.
D'abord.
On peut y aller? C'est bon? Okay. So, Armand, the committee has deliberated. We have appreciated quite a lot your presentation. It was very dynamic and covered a large range of topics. We prepared a draft report which has to be improved in the next days, but I can already read what we have written. So I'm switching to French because the report is written in French. So, Armand Kassaï a présenté avec beaucoup de clarté et dynamisme ses travaux de recherche sur les opérateurs neuronaux pour la résolution d'équations différentielles au dérivé partiel pour la physique. Le candidat a détaillé plusieurs algorithmes innovants visant à lever des verrous majeurs dans ce domaine. Ses contributions portent notamment sur la capacité des modèles à s'adapter à des variations de paramètres, de conditions initiales et de géométrie. De plus, les approches proposées intègrent efficacement les changements de topologie et finesse de la grille, tout en assurant un apprentissage et une inférence efficace, améliorée, parce que la répétition, sur des trajectoires densément discrétisées. Une comparaison rigoureuse avec différents modèles de l'état de l'art a démontré des gains significatifs en précision et efficacité computationnelle, ouvrant la voie à l'application de ces modèles à des problèmes du monde réel. Le candidat a répondu avec aisance aux questions très diverses posées par les membres du jury, démontrant ainsi sa maturité scientifique et son excellente maîtrise des subtilités techniques d'un domaine difficile et en très rapide évolution. Pour toutes ces raisons, alors, le jury vous confère le grade de docteur de Sorbonne Université en informatique. Voilà. Du coup, je ne sais pas si vous avez choisi de prononcer le serment suite.
Alors, en présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Alors, j'aimerais adresser quelques remerciements. Je suis désolé, je vous emmène voir un tunnel, mais ça rend.
Il y a du Bluetooth à faire en français.
So firstly, I would like to thank you for being here for my PhD defense. And I'm very excited to start working with you, so thank you for everything. I'm sorry for the rest of the things, I will keep going in French. J'aimerais évidemment remercier le reste du jury, notamment Marc et Gilles, pour vos précieux conseils et vos critiques constructives, et pour avoir évalué une thèse. J'aimerais remercier mes encadrants, donc Jean-Noël et Patrick. D'abord, Jean-Noël, j'aimerais te remercier. Bon, c'est vrai que depuis qu'on a déménagé, on n'a pas pu se voir autant, mais merci pour ton aide sur mon premier papier, sur GEPS notamment. On était encore au LIP6. Et merci pour les vacations. C'est grâce à toi que j'ai pu donner quelques cours, et je suis que je ne suis pas fan de cours. Voilà. Merci pour ça. Évidemment, un grand merci à Patrick. Merci déjà de m'avoir pris sous ton aile. J'ai beaucoup appris grâce à toi. Je sais que c'était un peu dur jusqu'à GEPS, et depuis GEPS, j'ai senti que tu m'as fait énormément confiance, donc vraiment, je te remercie beaucoup pour ça, parce que j'ai fait beaucoup confiance en moi grâce à toi. Et tu m'as donné énormément de ressources pour réussir, que ce soit via les collaborations avec les autres doctorants. Et puis tu m'as même laissé un peu t'aider dans la supervision de certains projets. Donc, merci beaucoup. Je sais aussi que tu as été présent. Parfois, j'ai été un peu. Je pouvais changer d'humeur, notamment les veilles de deadline, où je peux m'énerver, je ne me rappelle plus rien de moi. Et je sais que tu m'as jamais tenu rigueur, donc je te remercie beaucoup pour ça. Et même au niveau de l'actualité, tu as toujours été présent pour moi. Merci. J'aimerais ensuite remercier l'équipe Spatio-Temps. J'ai commencé par Johan. Merci beaucoup pour ton aide sur GEPS et pour tes précieux conseils. Je pense que tu m'as beaucoup aidé pour mon premier papier. Et je remercie le GOAT, oui. Je ne crois pas qu'il est là, mais s'il est là sur YouTube, merci pour toutes ces collaborations, que ce soit sur tes papiers ou miens. J'ai énormément appris grâce à toi, que ce soit dans les débats, les discussions. Tu m'as vraiment forgé un esprit critique, donc merci beaucoup. Merci beaucoup. Merci beaucoup à Lise, ma partenaire durant la thèse. On a vraiment fait équipe durant les 3 ans, et j'ai énormément apprécié de travailler avec toi. Tu le sais, j'ai adoré nos collaborations. Je voulais te remercier aussi parce que j'ai plein de beaux souvenirs grâce à toi, que ce soit notamment les veilles de deadline. Étonnamment, je vais m'en souvenir sous fond de Disney en nuit blanche au labo. C'était bien sympa. Et voilà, je pensais venir en thèse, j'avoue, un peu en faisant mes recherches dans mon coin. Et je repars avec plein de collaborations avec une amie, donc merci beaucoup. Ensuite, j'ai une liste énorme. Je remercie Jorge. Merci merci Jorge pour ton aide sur GEPS, et aussi pour m'avoir laissé explorer ta recherche avec toi sur Tornado. Merci aussi à Biel et Josfran pour avoir laissé diguer un peu avec vous la multiphysique. Je sais que le dernier projet va mener à son bout. Accrochez-vous. Et merci à Emma et Jarno aussi pour me laisser travailler avec eux sur vos idées de recherche. J'adore travailler avec vous. Ensuite, j'aimerais remercier les permanents et les autres doctorants de manière plus générale. Merci à vous pour ces 3 belles années. Petite dédicace aux gens du ski, où j'ai fait de très belles rencontres. Je pense notamment APA, Loïc et Victor, que j'ai appris à connaître vraiment là-bas. Et évidemment, je veux remercier un peu plus précieusement mes amis du labo, qui j'ai fait théâtre, ciné, festival, bref, plein de choses. Je pense notamment à Théo, Tristan, Lucas, Raph, Lise, Louis et Max. Donc, merci pour vous, merci d'être là. Un grand merci à Christophe, évidemment, mon ami. Merci pour toutes ces années. Merci d'avoir été là pour moi. Tu m'as beaucoup aidé. Ensuite, les amis. Alors, on commence par la maternelle. Merci. Bah, voilà, il y a Fissam et Kylian, et aussi d'autres Nour. Je pense notamment à Nour. Je suis trop content que vous soyez là à ma thèse et qu'on soit encore en contact, qu'on soit encore amis après toutes ces années. Ça compte beaucoup pour moi. Je remercie mes meilleures copines de Garches. Je pense à Chloé et Camille, qui ne peuvent pas être là pour des raisons évidentes. Je pense beaucoup à elles. Merci pour ce week-end en bas Florence, c'était trop bien. Merci aussi aux gars qui sont là. Je pense à Mathieu, oui, et Tristan pour ce week-end où c'était très marrant le maquillage, mais j'en fais des cauchemars. Euh, Merci aux amis du collège et du lycée. Je pense à Pierre-Louis, Guillaume, Pierre, Gabriel, tous les amis qui sont dans le cercle. Fanny, Simon, Claudine, Julia, Louise et Sandro. Merci beaucoup pour votre présence de toutes ces années. Évidemment, une grosse dédicace quand même à cette EVG de légende en Thaïlande, où je me couche à 4 heures du matin pour travailler sur Enma. Donc, ça m'a mis un spotlight, donc la vie est belle. Hein. Merci beaucoup à Pierre-Louis de m'avoir choisi pour témoin, ça m'a vraiment fait beaucoup plaisir. Ensuite, les tontons, Goldinger, merci beaucoup d'être là. Il y a même des têtes que je vois jamais et qui sont déterrées à venir. TSO, évidemment, à Hamza pour les games de LoL pendant la thèse. Merci beaucoup. Mes copines de l'escale aussi, meilleure barre du monde. Mariam et Kaina, je vous aime d'amour. Merci d'être dans ma vie. Ça a toujours été facile de vous parler quand ça allait pas bien. Évidemment, je remercie les familles Mousseni et Razani. Vous avez été là depuis que je suis petit. Donc, je vous remercie beaucoup pour vos gentillesses. Pardon. J'aimerais remercier 3 personnes en particulier. Je pense d'abord à Tanguy. Merci beaucoup pour tout. Merci, enfin tu sais, mais t'étais ma source d'énergie au labo. Donc je pense que je serais pas venu autant si t'étais pas là, je t'avoue. Donc merci beaucoup. Merci, enfin maintenant t'es même pote avec mon meilleur pote. On va encore ensemble, c'est incroyable. Vraiment les refs. Et tu sais que indépendamment du fait que tout le monde dise qu'on se ressemble de ouf, même si je sais pas où sont mes beaux yeux bleus, t'es vraiment devenu un ref pour moi. Donc voilà, ça je fais. Ensuite Agnès. Je voulais te remercier parce que tu as toujours été un soutien inconditionnel pour moi quand j'allais pas bien. Hein. Je pense notamment en Corse, où j'étais un peu au plus bas. Et tu as fait en sorte que je fasse de très bonnes vacances. Donc merci beaucoup. Je sais que parfois j'étais un peu absent et tu as beaucoup alimenté la relation. Donc, voilà, je m'excuse pour ça et merci beaucoup d'être mon ami. Et enfin, Enzo, je ne peux pas dire, hein, je ne te lâche pas depuis 25 ans. Même quand tu étais à San Francisco, dans le pays du Chétan, on était sur Discord tous les jours. Donc voilà, je me couchais à 3 heures du matin, je niquais mon rythme, mais mon meilleur pote était toujours là. Donc voilà, t'es une source d'inspiration pour moi et j'ai la chance d'avoir un ami comme toi avec qui je suis autant aligné sur une système de valeurs. Et enfin, je veux remercier ma famille. C'est 4 années, elles ont été dures. On a connu maladie, opération et actualité compliquée. Vous avez toujours fait en sorte que ma thèse elle se passe bien. Donc merci beaucoup. Je voulais remercier mon frère parce que t'es vraiment un modèle pour moi, que ce soit dans le style, intellectuellement. Enfin, j'ai toujours cherché à te copier. Et voilà, j'ai l'impression que ça me réussit bien, donc merci beaucoup. J'aimerais remercier mon père, parce que tu as toujours cru en moi, alors que je n'étais pas l'élève le plus assidu à l'école. donc je préfère jouer, quoi. Merci pour m'avoir inculqué les valeurs de discipline et de travail. Tu as été un exemple et tu continues à l'être. Et je suis fier d'être ton fils. Et merci ma mère. Merci d'être aussi tendre avec moi, de m'avoir appris à me comporter bien avec les gens, d'être toujours aussi occupé de moi. Merci pour tous ces dimanches où c'était facile. Enfin, je venais, c'était très haut l'accent. Tu me faisais les meilleurs plats iraniens. Donc voilà, enfin, j'adore manger. J'ai de la chance d'avoir une mère comme ça. Et voilà, je serai toujours là pour toi. Et je vous aime très fort tous les trois. Et je voulais dire un dernier petit mot à ma femme Mignon, qui vit des moments difficiles. Je voulais leur dire que voilà, je pense beaucoup à eux. Je pense notamment à ma grand-mère qui aurait aimé être là. Ma grand-mère me disait toujours 3 phrases quand je l'appelais, donc je l'appelais tous les dimanches. La première, c'est quand est-ce que je lui présente une femme et les enfants, impossible. Quand est-ce que je lui présente, enfin, quand est-ce que j'ai le permis? Et la troisième, et quand est-ce que j'ai le doctorat? Et donc voilà, j'ai le doctorat. Donc, voilà, merci beaucoup à vous. Merci d'être là. Il y a un point en haut où je présente la culture iranienne et française. Donc voilà, on va bien manger. Donc rendez-vous en haut à Skype. Merci. Je vais faire un cadeau.
Voilà, vas-y.
So I will let you, Gilles Lu. Thank you for your presentation. And have a good afternoon.
Okay,
Oui.
thanks a lot.
Félicitations.
Merci
Profite bien.
beaucoup.
Thank you, see you.
Salut Patrick.
Salut.
Ouais, alors Sky, vous montez les escaliers et vous allez sur votre droite, vous allez tomber sur Sky, il y a de la bouffe. J'arrive.